7 is up, daily work, what we're doing every day. We've got a lab today, solutions, suspensions, and colloids. We're also going to be working on lecture today. Test for this unit is going to be available from the 7th to the 13th of February. Today is your last day for Unit 6 for the test, so make sure if you haven't taken it, you will take it. And a lot of you have been asking what is lab setup or lab whatever on your grade. Remember, you have to give me 1 half-hour period where you help me set up or take down labs this term. And I'm giving it to you as a lab, so you get the 100 points for coming in and helping. And then you can make up extra time or extra labs, so you can do come extra times, 20 points a time, up to another 100. Okay, so that will be up here for every week. I'll put them up there, watch it. It might change daily. If we don't get a lab set up, I need set up, I might put another one up. I will do some before school, after school, and some during tutorial. So watch that. Okay, you just need to, you have to have one. And it's your choice if you want to come to more. I will also be putting, when I will not be here after school, most Tuesdays I will not be here after school, right after school, but there might be other days that I've got training today and have to be in Mrs. Barney's room after school for 2 hours. I'm putting my happy face on. Okay, English teacher. So we are going to get started today. There are 3 labs in this unit. We're going to be doing a pre-lab for one next time, and then the lab, a pre-lab for the one after that, and it's going to take 2 days. Okay, so we've got some fun coming up. All right, so today you should have taken quiz 7.1. I'm going to be telling you each day this is the sapling you should be on. You should have some time each day to work on it. Today you'll have about 20-30 minutes at the end of the period to finish your lab notebook, to work on 7.1, whatever, wherever you're at. Okay, remember that quizzes are due today for 6, and sapling, just that one sapling, the review sapling is due today. Okay, so onward we go. So first thing that we're going to talk about a lot is the vocabulary for this unit. The vocabulary for this unit, there's a lot of different things that mean the exact same thing. So we'll talk about each one as we go. As we talk about a solution is made up of a solute and a solvent. The solute is what is being dissolved. The solvent is what is doing the dissolving. And a solution is made up of a solute and a solvent. Okay? When we talk about dissolving, what's happening is the solute is being surrounded by the solvent and being pulled apart and making a solution. So that's down on the lower left side. The solution does have different properties than the solute or the solvent itself. Okay, so solute is what's being dissolved, solvent is what's doing the dissolving, and a solution is made up of a solute and a solvent. Okay, so let's talk about this. So we need to be able to look at something and say it's a solution or a non-solution. There are several different things that are non-solutions. Okay, foggy air is actually not a solution. Okay. Tears are a solution. Maple syrup is a solution. Milk is not a solution. And creamy hand lotion is not a solution. So we're going to have to do some definitions here because 2 of those, milk and creamy hand lotions, sound like they should be solutions, but they're not. And we'll go a little bit more into classifying what is what. Okay, so most of you know this verbology. Soluble means it's going to dissolve. Insoluble means it's not going to dissolve. But we're going to be using some words that mean the same thing but are different. So as we talk about solubility, insoluble, we're also going to be talking about miscible and immiscible. Basically the same thing. If something is miscible, it's soluble. If something's immiscible, it's insoluble. It's just a different verb to mean the same thing. So acetone in water that, is miscible. Another example of that would be your isopropyl alcohol or your rubbing alcohol you get from the store. That's usually ethanol or isopropyl alcohol dissolved in water. So those are miscible. Something that's immiscible, something that you would be more familiar with than water and methylene, would be like oil and vinegar dressing. Okay, yes. All it means is mixable or not mixable, basically. Okay, so if you can mix two solids and make a solution, that does happen. This is something that I pulled from, remember when we did, I'm going to do these a little bit darker so you can see them. When we did the lab, when we were trying to figure out if there was precipitates or not, remember that lab? I did a screen capture and they did not show up very good, so I'm sorry about that. This is that last screen. I didn't want to show that again, but if you wanted to see that video again, you just have to go onto YouTube and search NAGSAG. But these are the tricks to remember the solubility rules. And solubility rules, most often, these are always soluble. Nitrates, acetates, group 1 metals are always soluble. There's no exceptions. SAG, sulfates are most often soluble with the 2 exceptions on the side. Ammonia is always soluble, and group 17 metals are soluble except with PMS. PMS is lead, mercury, and silver, and sulfates are not soluble with lead, mercury, silver, and calcium, strontium, barium. So if you remember that, that saves you a lot of time to deal with solutions, which is the unit we're in right now. So this is sort of a reminder page, okay? As we go forward here, we need a little bit more definition because some things are more soluble than others. So this is a definition for, and I know I'm going to be flipping back and forth here because there's some things that aren't in order, and I'm sorry. If something is less than 0.1 grams in 100 grams, we consider it insoluble. And I forgot to change to blue, sorry. If it's between 0.1 and 1 gram that's able to be dissolved in 100 grams, then we can consider it slightly soluble. If it's between 1 and 10 grams for every 100 grams of water, we consider it soluble. And if it's greater than 10 grams in 100 grams, then we consider it very soluble. So there's going to be a lot of different verbology that we're going to need to be using in the solutions unit. Hopefully it'll click and you'll be able to get that a little bit better. We also need to talk about insolubility, 3 concentration verbs, and one is unsaturated. If I'm looking at a graph of things that shows me a line of this is the maximum amount that is saturated, how much I can put in without things falling out, then unsaturated would be below that line. In other words, I can put more stuff and get it to dissolve. Saturated solution is no more solid, it dissolves at that temperature. Okay, that's important. It has to be at a specific temperature. So no more solid would dissolve at that temperature. And then supersaturated is I've heated the solution. So this is like what when we make candies and usually like divinity and stuff, we heat a sugar water solution up so more sugar will dissolve in it, and then we slowly cool it back down. If you cool it back down too fast, you get crystals. But if you cool it down slowly, then you don't. That becomes a supersaturated solution. It's unstable. So if you wanted to make a really cool thing that you could show your friends and sort of fun, you take about 2 liters of vinegar and put 2 tablespoons of baking soda in it. You know what's going to happen. Put it in a large pot so it'll stay in the pot. Then heat it up slowly until it gets like a little thin skin on it. It takes a while and it stinks, but you get a little thin skin on it. Then you pour that into a clean cup and let it cool down. Don't touch it. Then what you do is you put just a couple crystals of baking soda on a plate and very slowly pour that, and it will make what's called hot ice. It will actually make a stalactite that keeps building and building and building. So that is what is inside of, have any of you used the reusable hot hand warmers that have the little metal thing inside of it that click? That's what's inside those, is saturated or supersaturated sodium bicarbonate solution. Okay, so it's actually acetate by then. So let's look at these things right here. We're going to use these terms to sort of go over how would we describe them. We've used a lot of verbs there, a lot of technical terms here. We need to have some terms that we could use for here. So if I have 25 milliliters of water, and yours is supposed to say 1 gram of salt, not 1 milliliter of salt, what would I term that? Well, if I remember my chart that had to do with how many grams would be in how many grams, it was 100 grams of water, which is 100 milliliters of water, right? So that's like 4 times what I've got right here. So I'm going to 4 times it. So 100 grams of water, and that would be 4 grams of salt. So what could I classify that as? Soluble. So this could be classified as soluble. As we look at the next one, I've got this many grams, which is really small, in that many grams of water. What would that be considered? That would be considered soluble? Insoluble, yes. Sorry, I didn't hear the in. Insoluble. Now, don't get caught on the last one because we're not using the same terminology, but how would I describe the next one? When a solution, when a small piece of solid is added, causes more solute to come out of solution. We just talked about that. What kind of would that be? What would it be? No. Supersaturated. Okay, this would be supersaturated. This is the one that when we click that disk, it turns solid. Saturate. I did not spell that right. Try it again. Saturated. There we go. Okay. So here I've got a beautiful graph that has lots of different chemicals on it. Most of them increase in solubility as the temperature increases. There's one that does not. Which one is it? Cerium 3 sulfate. Okay, cerium 3 sulfate. That one actually becomes less soluble as the temperature goes up. There are some chemicals that do that. So as we're looking at this, so we need to be able to read this graph. This is another ACT kind of thing. So if I'm going across at 55 grams, that's on the left, and I hit the KNO3, okay? So 55 grams, I'm coming across, and I hit the KNO3. But it says at 35 degrees, I'm going to come up. So 35 degrees, I'm going to be right on that line. That didn't draw very well, but I'm going to be right on that line. So what did I tell you about the line? How would I describe if I hit right on the line? Saturated. Yep, so this would be saturated. Okay, then we grab another one. At 30 grams, so here I'm going to cut across at this level, and 50 degrees, coming up at this one. So I'm coming across, and I'm coming up. And I'm looking for potassium dichromate, which is the gray line. I'm going to hit, it looks like, basically on it again, right? So I'm going to say this is saturated again. Okay, let's do 10 grams right here and 60. So I come all the way over to 60 right here. And I'm looking at cerium 3 sulfate. Where am I? I'm where? I'm below it? Above it, because it's a light blue line. Okay, so I'm above it. So what does it mean when I'm above it? If on the line is saturated, I'm supersaturated. So this one would be supersaturated. And unsteady, unstable. Okay, then I go to 82, which is just a little bit above 80, and I'm coming up at 10 degrees. So I'm going to hit right here, and I'm looking at sodium nitrate. What am I? Above, which means it's going to be supersaturated. My marker does not work down there, so I'm just going to put an arrow. That's also supersaturated. So I need to be able to look at a graph like this and be able to read off, am I saturated, supersaturated? If I was underneath, it would be unsaturated. Okay, so for instance, if I took this 30 and 50 right here, and I was comparing KCl, which is the hot pink one, I would be unsaturated. Okay, all right, going forward. So, determine if the following are miscible or immiscible. What was immiscible and miscible again? Mix or don't mix, or soluble or insoluble. So I have 25 milliliters of cooking oil and 25 milliliters of vinegar. The resulting mixture is cloudy and slowly separates. Immiscible. Okay, meaning it won't mix. Okay, I have 25 milliliters of rubbing alcohol and 25 milliliters of water. The resulting mixture is clear and colorless. Miscible. Okay, I have 25 milliliters of chloroform and 1 gram of roofing tar, and the resulting mixture is clear but dark brown in color. Miscible, good. Okay, so being able to describe what I'm seeing and being able to give the term to it, good. All right, so now we get to colloids, and I don't know exactly where this is in your stuff, so we're just going to shoot with it because we're going to go through it today. We need to know, colloid is just sort of in between. So solution particles are so small that light does not catch them. Colloid particles are a little bigger, particle size between, so this is what we need to know. This is solution. So anything less than this size particle is going to be a solution. This is colloid. Anything between this is going to be a colloid. And this is a suspension. And so I need to know what size a suspension would be. Okay? Colloids don't separate. Okay, a colloid is big enough, the particle's big enough that it will catch light, but it doesn't separate out. Suspensions will separate out. So it's like that oil and vinegar dressing, or like if you ever were sick when you were a kid and the doctor gave you that pink medicine, mom had to shake it up every time before they gave it to you, amoxicillin. That's a suspension. Okay, so it doesn't stay in solution. Colloids don't separate. The particles aren't trapped by a filter. A suspension, I can trap the particles with a filter. But colloids are small enough they go right through the filter. Okay? Both colloids and suspensions appear cloudy, unlike solutions, which are usually clearer. And colloids and solutions will not separate into layers, but suspensions will. Okay, so let's look a little bit farther. How do I tell the difference then? This is what's known as a Tyndall effect. If you've ever got up on a foggy day and you've gone outside and you turned on your headlights on your car in the fog, what happens? It scatters all over, right? It lights a whole area up. It doesn't show you the road really well. It shows everything else as bright. That's because the particles are big enough that they can scatter light. So if I take a flashlight and shoot it through a colloidal solution, it will scatter and light up the whole thing. Okay? If I take it through a true solution, which is right here, this is a true solution, all I'll see is where the light entered the glass and where it exited the glass. I won't see the pathway it took. Like here I can see the pathway it took, and it lit up the rest. Okay, because light was scattered. This is known as a Tyndall effect, and you're going to be looking for that in lab today. So it's either yes, it has a Tyndall effect, or no, it doesn't. Yes? Particles are big enough to catch the light. So both colloids and suspensions will show you a Tyndall effect. How can I tell the difference between a colloid and a suspension, though? What was the definition of a suspension? This is the awkward silent time. Yes? You can filter something out, good, or it will settle out over time. So for instance, if I have a suspension like the amoxicillin, it'll settle out and be at the bottom, and the water would be at the top, so I'd have to shake it up again. Like the vinegar and oil, I have to shake it up again so it stays in while I'm pouring it, rather than just getting the oil or the vinegar off the top. Okay, so fog is a Tyndall effect. That picture did not show. If you've ever been in the forest, though, and you see the light coming through the forest, you can actually see the pathway that the light takes, that's a Tyndall effect. Okay? So over here, we've got a couple of things. We've got dispersing media, and we've got dispersing phase. Dispersing media is like the solution. It's like the solvent. Okay? This dispersed phase is like the solute. Okay, so dispersing media is like the solvent. Dispersing phase is like the solute. Okay, we've got different kinds of colloids that we can work with. Besides fog, we have smoke, we have whipped cream, soap, milk, mayonnaise, paints, clays, gelatins. If you're just turning it in, just turn it over here. No, not right now. Sorry. We've got marshmallow, we've got butter, cheese, and we've got ruby glasses, okay, that we can use as far as different kinds of colloids. Okay, going forward. Sometimes it's hard to get them to stick together. We have to use what's called emulsifying agents. And emulsifying agents sort of get nonpolar things and polar things to stick together because they're the in-between. So it's like having two friends that don't get along and you're the in-between friend. You're trying to keep peace kind of thing going on. These are used a lot with soaps because we want to be able to clean fabric that has oils on it and that has sweat that is more ionic. So we have to have a polar end and a nonpolar end. So we use emulsifying agents. Okay. They're also stabilizing agents. So for instance, if I had mayonnaise, if I don't put a stabilizing agent or an emulsifying agent in there, then it will separate and be nasty, and we'd have to keep whipping it up and keep whipping it up. So we have to do that to stabilize it. Soaps and detergents also need that, and we talked about that. Okay, so here comes some more verbiage. In a solution, we just have the solute and the solvent. But in a suspension, we have what's called the supernate, which is the liquid above, and the precipitate is the part that falls out. So in a suspension, for instance, if I took some river water, a sample of river water, and just set it to the side, I would actually get clear water on the top, and then I would have the dirt that would fall out at the bottom over time. Some examples of suspensions we talked about were the oil and vinegar dressings. Coffee or tea with milk would be a suspension. And we already talked about salad dressing. Milo drinks will also do that. We did talk about the Tyndall effect down there at the bottom. Both colloids and suspensions will show Tyndall effect. But remember to tell the difference between a colloid and a suspension. The suspension will eventually fall out. You'll separate. The colloid will not. Okay, yes? Okay, when we have a solution process, this is known as salvation. Not salvation, but solvation. What happens is you have a hydrated ion. And the ion can be positive or negative. And a hydrated ion, you're basically surrounding it with water. And remember, water is a polar molecule, so it has a positive and a negative side. So if we're looking at the cation here, I've already drawn on here positive and negative. Remember that one side was positive, one side was negative. The oxygen was negative. Hydrogen side was slightly positive, not a full one. But it will surround a cation with the negative side of water. It will surround an anion with the positive side of water, which is the hydrogen side. Okay, so you have a place where you get to draw this in. So I'm going to give you a few minutes to draw this because it takes a little bit of time. You'll notice on the upper right-hand side, I've also included a hydration or a hydrated ion, and it's from the MCAT review. So it's something that you need to go on with the MCAT. Yes? Definition of a hydrated ion is just an ion that is surrounded with water. So an ion that's surrounded with water. And then depending on if you have a cation, which is a positive ion, or an anion, which is a negative ion, it depends on what side of the water goes in and which side goes out. And the one on the right-hand side sort of shows you more with the size. Remember, a negative ion means it's got an extra electron, so it really can't hold on to it. That's why it's bigger. A positive ion's given away an electron, so it's becomes smaller and tighter. Okay, looks like most of you are done. You go forward. So a good rule of thumb to know, now you've got to be careful with this because if you use this on the test, it will be wrong. But think in your head, like dissolves like. That means polar will dissolve polar things. Non-polar things will dissolve non-polar things. But do not use like dissolve like. Just use it to help you remember. Okay? So for instance, a little cartoon over the side. Help, help, I'm dissolving, but bears are insoluble. That's easy for you to say. You're not polar. So water's polar, polar bear, haha. Okay? So non-polar would be the brown bear. He doesn't have that polar edge. Over here on the right, or on the left side, I really like this graphic here because this would be like a salt crystal. And what happens when the salt crystal starts to be surrounded with water is if it's a chlorine ion, you'll notice that the hydrogens are facing in towards the chlorine and the oxygens are away. That's a hydrated anion. Down here at the bottom, the sodium would be taken away by the oxygens, and the oxygens surround it with the hydrogens facing out. So that's how we dissolve. That's known as salvation, or salvation, not salvation. Okay? All right, down here at the bottom here on the right, we've got dissolving process. The intermolecular forces like dissolves like. So on the left, we've got ethylene glycol. And ethylene glycol has a hydroxide that makes it a little bit polar. So it will dissolve in water. And ethylene glycol is antifreeze. Okay? On the right here, we've got oil and water. And oil, it doesn't have the extra oxygen, doesn't have a polar there. So it will stay above the water because like, it's not like, it's unlike each other. Okay? So be careful not to confuse solubility with the rate at which a solvent or solute dissolves. Some solids take a long time to dissolve, but they will dissolve a lot in there. So this next part, there's 3 methods to increase the rate at which something will dissolve. I call them my Kool-Aid rules. Okay? So if I want to make Kool-Aid really, really fast, not saying that it's going to be good, but going to make it really, really fast, then I'm going to use hot water. I'm going to use the smallest sugar I can possibly, powdered, and I'm going to stir it like crazy. Then I can make it really fast. It's not going to taste real great because it's going to be hot Kool-Aid, but it'll be made. Okay, unlike my kids when they were little, used to make Kool-Aid, they would dump 2 cups of sugar in instead of 1. They would then dump the Kool-Aid pack in, and then they would pour you a cup. They wouldn't stir it. So the first glass was really sort of nasty. It didn't have much flavor other than the flavor pack, and it was really sour. By the time you got down to the bottom, it was basically sugar. Okay, so if you want to speed something up, the rate at which, and we're going to be doing some rate stuff coming up, heat it, crush it, stir it. So smaller particles, higher temperature, and stir it. That works for most of them. Remember, we had that one chemical that didn't like the heat. It would be better in cold. So those are some things to think about there. Okay? We're still working with our exo and endothermic. So remember these graphs. We start with our reactants. We have our activation, or E of A, from the reactants to the top of the curve. At the top of the curve, we have our activated complex. Remember, that's the Grinch sled. Which way is it going to go? And then at the bottom, we've got products. From here to here, this is a delta, negative delta H. So this one is an exothermic reaction. This other one, positive delta H, endothermic reaction because I end up above where the reactants were. I still have the E of A, I still have the activated complex. Okay, another way you can think about it, reactants with products for exothermic, heat energy is being released. Endothermic, I've got to pull heat in. This one's going to feel cold or cooler. This one's going to feel hot. Okay, so we can do some things there, but we've already done these curves, right? We know these curves, yes?
So, just looking at an equation, how could you tell if it was either one?
So, if I'm looking at an equation, usually in an equation, it will have, for exothermic, plus so many kilojoules. Or it will have delta H equals a negative something kilojoules. For endothermic, I'll have this plus some amount of kilojoules yields this. And that would tell me it's endothermic, or I'd have delta H equals a positive something kilojoules at the end of the reaction. Okay? Any other questions there? We okay? So this is sort of mixing in with the last unit a little bit here. Okay. That's the end of lecture notes for today. So what I'd like to do is really quickly go over lab, and then I'm going to send you back to lab. Lab does not take very long, especially if you listen to how I tell you to do it, and you do it really quickly. It does not take long. You finish back there, get a stamp, you can come back in here. The rest of the time is for you to work. So when you go back to lab, you are going to have a rack of test tubes, okay? Please do put whatever you're supposed to put in the test tubes before you put the distilled water in. It just makes life a lot easier. Okay, so for instance, I'm putting a pinch of salt in, I'm putting a little dirt in, I'm putting so many drops of milk in. There's two of you in a group. We've got one that you just have to go with these guys or these guys. Okay, one singlet. Divide up. There's 5 test tubes. One of them is just distilled water. You don't have to do anything with it. So that means 2 test tubes each. One of you go get milk, one of you go get oil. The other one go get dirt and get salt. Okay, or however you want to divide it. Bring it back. Then you want to fill it, this line right here is fill it with distilled water to the same level, all the way across. Take your initial observations. Shake them. Observation. Then I'm going to turn the lights off because it makes it a lot easier. You're going to take a flashlight and you're going to shine through it. Does it give you a Tyndall effect? Does it light the thing up? Or doesn't it? If you're questioning it, it's probably a no. If you can just see the light going in and the light going out, but you cannot see the pathway through, it's a no. Okay? Once you're done with that, dump out the salt and the milk in the sink, but dump out the dirt and the oil in the garbage can. And then wash the test tubes, hang them upside down, get a stamp, and you're back in here. Okay, any questions? Goggles are mandatory because we are working with glass. Okay, sorry. Back in the back. We're in the very back lab.